going to talk to you about using PMM to troubleshoot and optimize MySQL performance. Now, you probably have already heard about PMM on this conference, but in a nutshell, what Percona Monitoring and Management, or PMM, is our monitoring solutions for MySQL. And as the name implies, we also have an ambition to extend it to be a management solution later down the road, but well, we're not quite here yet. What is important about PMM is that it's 100% free and open source database monitoring solution, which you can roll your own, and you can use to monitor MySQL both on a premises environment as well as in the cloud. And in the cloud, that means that it both works with your kind of roll your own as well as database as a service environment. Now, one thing that is also important about PMM, what it is not really built by Percona and Percona alone from scratch. We are using the really industry-leading components which are used by people to use those kind of applications. We use Grafana, for example, for visualization. We use Prometheus as a time series data store. And those are wonderful because that means you can use a lot of tools, extensions from the ecosystem, right? Not just what we have implemented, right, and only with a small ecosystem out there. Okay. Now, if you want to learn more about the PMM, you can either get it from using this link I show here, or we also have a website called pmmdemopercona.com. It has it deployed on maybe 30 instances or so, right? So you can see how it works with MySQL, with Percona XDB cluster, with MariaDB, with MongoDB. So that is a very good way to play around with if you don't want to install it just yet. So what we're going to do in this presentation is really to look at some of the common issues with MySQL and how you can use PMM to use them. Now, it's worth to note what PMM is not just about MySQL. It supports MongoDB as well. You can also add many other databases and actually other monitoring sources through our support through external exporters, right? You can take pretty much anything Prometheus support, plug it in, get a dashboards from Grafana network and extend it this way. But this presentation is going to be MySQL focused. Now, when you're looking at MySQL optimization and troubleshooting, I assume one of those few things apply. A, you often just want to have your MySQL server to run queries faster, right? That's a pretty common desire. You also may want to troubleshoot sudden MySQL performance problem. Your MySQL was working very well yesterday, and today it's slow, queries run slow, developers complain, application doesn't work well, right? That's a possibility. And also, often you may want to find a way to run more efficiently, use less resources. Right? Especially that is important in the cloud, when that can go directly to your pocket. If you can scale down your instances or reduce their size, then you can start saving money today, right? Those all three things I think often come very much together through a performance optimization troubleshooting angle. Now, if you look at the MySQL performance, I believe there are two different ways you can approach that from a high level. From one standpoint, you can think about that from a query-based approach, right? You can say, hey, if you look at the MySQL from my application black box, application sends queries to MySQL and gets a response after certain processing, right? If you look exactly where that processing time goes, we can really understand what is going on, why the queries are slow, right, and deal with them. Right? And that is how you can troubleshoot very well specific applications, maybe specific features in the application, like, oh, this page doesn't load well, right, to look at that for these features and go and drill down to the queries. And then another approach is to look at that is through a resource-based approach, right? Because you can think in the end, we have a hardware resources, right? And whatever workload you push on MySQL is going to use those resources. Understanding how those resources utilization, saturation happens, you often can have overall optimizations, right? That's how you, for example, can reduce cost. And often that also would impact your overall performance. What are the primary resources we are talking about? When it comes to MySQL, right, and in general, you can be thinking about those 4 primary resources which you have to be very mindful about their use and consumption. Now, it is important to note what if you're looking at the resources and none of them is used 100%, and you still have a poor performance, it is still very much possible, right? So we cannot say, oh, you know what, unless my CPU or disk or network is used 100%, right, then that means the problem is somewhere else. There are things like contention, you know, table lock, row-level lock, some internal mutex contentions which can very much show us what there is a lot of free resources available, but because of that internal limitations, you have a performance being limited. And also another thing which you often see a lot is what you can think about as a mixed resource usage, right? If you think about the process which, for example, read from a disk, then it's kind of did some process on CPU and then sends the data from network, right? From a time standpoint, you may be seeing a third and a third and a third. And if you look at resource utilization, you can say, hey, you know what? Nothing here is completely saturated, but overall, right, you are being bound just on a different resources and different time. So one of the very common metrics which we use in the Linux performance management is load average, right? So we have this graph of load average. What guys you can tell me about the server? By looking at this load average graph, any, what's that? Well, now, so in reality, it is hard to say something meaningful from load average alone. The thing with a load average, especially on Linux, is multiple fold. One is load average is really mixes CPU weight and I/O weight. Right? So for example, you may have a long run queue. In the previous case, you may have a lot of outstanding IOPS. They're all mixed together. It's also not really normalized, right? In this case, you can say, wow, that is a lot of, you know, load average is high, but if I tell you this process has, you know, maybe 100 cores, right? The server has 100 cores, then, you know, 40 runnable processes, right, would not be very a big deal, right? And also it doesn't really look at the queue depth for storage, right? The queue depth for storage, I think, is the most complicated thing in terms of Linux performance monitoring, because while we can know how many distinct CPU cores and threads we have, right, that information is readily exposed, but if you look at your I/O storage, how many parallel queues are out there, right, and how many I/O requests it can really process in parallel without queuing, you don't really know, right? You can only observe that through increase in the latency, right? So this is an example of a CPU usage, right, which corresponds to this graph. And what we also show in our tool in this case is the saturation metrics, right? In this case, when we essentially take a look at the load average and kind of really split it between CPU and I/O workload saturation. Right, so in this case, we can look at the I/O load, right, which corresponds to pretty much how many I/Os are being kind of in average, right, where at that point period of time. And you can see what that system is pretty significantly I/O bound, right? Even though you don't see a lot of CPUs stored in an I/O wait state, right? Now we can see what the CPU load in this case is not very high, especially if you normalize that, right? If you can say the ratio of our runnable processes to available cores is actually pretty relatively low, right? It's less than 1, so there is not high saturation happening. So from this graph, that means I can see what, if anything, my system is more loaded in the I/O stage than CPU. Now, another thing it's good to look at is obviously row-level logs. Row-level logs, that is a logical contention, but that pretty often can be limiting the performance limiting factor for that. And in this case, we look at number of areas, right? We can look at the number of row log weights, how much how many log weights happen. And what I like to especially look at the row log weights is this metric which we call row log weight load. That pretty much corresponds to how many processes were blocked through proceeding because we have been waiting on the row level logs, right, at this point in time. And in this case, we can see what in average, right, I have again, maybe 2 or 3 processes blocked, right, by row level log. And that gives me the idea to what extent that is being a problem. Now, if you like load average, it's also quite nice to think to know what the MySQL provides somewhat comparable metric on the MySQL side, which is called number of threads running. Now, threads running is pretty coarse in terms of it says how many connections have a data being processed on the MySQL side. It doesn't make a difference wherever it's what that processing means. It may be processing because it's running on CPU, maybe waiting on disk I/O, maybe even waiting on row logs, right? But in general, that is a very good number to understand, right, and observe, because when you have a huge amount of threads running Spike, you're trying to process a lot of transactions at the same time, often a lot of problems exaggregate, right? You may often would see a lot of internal contention going on. You would often have a lot of those transactions running at the same time, having a lot of row level logs and so on and so forth, right? So spikes in threads running often correspond to some problems in the system, right, or problems in the system waiting to happen. In this case, we actually plot you both the average number of threads running, right, but as well as those red graphs show spikes, maximum number, right, in this case, because both of them are good to understand. Spikes every so often is not a big deal, but it gives me a good idea to zoom in that graph, because if I had, let's say, spike for example, 5 seconds, 10 seconds, that is often where we see the starting to show some problems. Another thing I like looking at is MySQL questions. The MySQL questions, that is, pretty much shows us inflow of questions, right? How many questions are being accepted by MySQL from a client. And spikes and dips, in this case, are pretty important figures, right? If you have a spikes, then the question is why, right? Maybe there's some application workload changes, right? Maybe some, caches malfunction, right? Dips is even more a good question to investigate, right? Because in many cases, your dips happen even if some problem on the application side, or maybe because of some slowdown on MySQL side, right? Which kind of really prevents those problems. I very much, yeah, go ahead. What's that? Oh, yeah. I mean, in this case, these are just some graphs, but by default, you would store, think about like a 30 days with 1 second resolution, so you can, zoom in any period of time. Okay, yeah, and that is like one, I would say, one of the first questions I like to ask. If you have a performance problem, I would like to ask you, hey, is it performance problem happening where you get more queries than usual or less queries than usual being processed, right? Because if it's more queries than usual, then I can say, well, you know what, likely it is application for some reason went crazy and sending much more queries. And of course, MySQL is not able to process them, right? If I have number of queries low, right, and there is a lot of such a problem, then it's often some internal problems. Let's say MySQL went crazy and now doesn't use proper execution plan, and because of that, even if you have a low queries, they each have much more time to process, right? So I think that is a very good thing to understand. Now, another good indication on MySQL side about the work which is actually being done is looking at the InnoDB rows. Assuming you use InnoDB tables, which I assume most of you are. We can see in this case how many rows are being read or written in a second. That corresponds to amount of physical work which is being done much better than the queries, right? Now, of course, not all row reads are created equal as well, right? You can have huge blobs which are multiple megabytes, or we have like some tiny rows. But in general, that is a very good indication. And in many cases, when you have something like a bad execution plan or some very complicated queries, you would likely have a spike in work being done. Another thing you can take a look at is commands, which shows us on a lower level what kind of, or on a command level, what kind of operations are being handled in this case. Now, note though there is a little inconsistency how MySQL does counting. It double counts prepared statements, right? So prepared statements are both counted as com execute and then com select or com update, whatever type of prepared statement that is. So keep that in mind. Now, another data that MySQL exposes is called the handlers. Handlers correspond to some low-level storage engine primitives, which are called. The good thing about those handlers is what they work for all storage engines. They also give us a little bit more information about the access type, because, for example, you can't maybe see very well, but like read next, that corresponds to index scan, and read R&D next corresponds to full table scans, right? So for those, I can really understand what kind of access patterns on the database my overall traffic employs. Now, the trick of handler calls, those, is they mix temporary and non-temporary tables, right? So which actually have a significantly different cost, right? So that's why you often used to use if combination something else. Memory usage for MySQL, that is obviously pretty basic. Like if you look at the general highlights, what we expect to see here is what you would have majority of operating system memory used by MySQL, if that is if that is their dedicated server, right? And you of course want to be careful not to overcommit too much memory, right? Because swapping out your database cache is not very efficient. And you can see in this case it shows us like number of different areas, but majority of that is used for buffer pool, right? And pretty much that is commonplace, and in real environment that would be even a larger portion of your system. Let's look at some InnoDB things in length, in depth, what you can see here. InnoDB checkpointing. right? That is a very important area for write-intensive workloads, right? I mean, if you don't have enough log space, then often your InnoDB will be doing too aggressive checkpointing and limiting your write performance. This graph shows us how much of an InnoDB log space used compared to that's a funny, okay. Yeah, it goes back and forth for some reason. I'm not sure why. And this is the total the amount of checkpoint spaces available. In this case, we don't really have a lot of pressure, right, on a checkpoint. In this case, we can see I have a significantly lower, smaller log file size for same workloads, and we can see it gets very close, right, and goes kind of back and forth a little bit, right, and that is indication that I'm having a lot of checkpoint pressure, and that's indication if I would increase my log file size, I would get a better performance. Another example, or another thing to look at in monitoring is a history length. History length shows how many unpurged transactions happen. And you would normally see things something like that, because wherever you run some sort of a long reporting queries, your purge process temporarily pauses, right, and you would have the history length slightly grow. What you want to make sure, though, is what you don't have many millions of unpurged transactions, or your kind of queue of unpurged transactions kind of constantly growing and never kind of drops quickly back like on the graphs here, because that would correspond to your purge system malfunction in some cases in MySQL, and which will cause increase in performance problems, right, as it processed. So this is actually that example, right? So here what I have done is I opened the session, right, started transaction, and I don't know, let's say, went to lunch, right? And you can see we can have our transaction history continuing growing unbound, right? That is example of bad behavior, right? Don't keep transactions open, right? Spot things like that and deal with them. Yeah. Now, what is a good thing, though, in this case, is you can see when I killed that transaction, my backlog was able to recover pretty quickly, right? So you see the slope of this curve? So that means I have a lot of capacity to clean up, purge the old data. If that would be kind of going like this very slowly, then that would indicate what my purge process is kind of operating close to capacity, right? And I may have problems in the future, right, with increasing load. Log buffer performance. What I think is important for to understand, many people do not recognize how little InnoDB log buffer space InnoDB may require in many workloads, right? I see people allocating, oh, let me set InnoDB log buffer size to maybe gigabyte, just in case, right, or something like that. Because InnoDB by default would flash log at every transaction, or in the worst case scenario every second, right? Unless you are really sending some huge monster blobs, you are not likely to require a lot of log space, right? So in this case, you can see even like 16 megabytes was more than enough, but 64 megs or so is good enough for majority workloads. Here is another way we can look at the login performance. What this graph shows us is three different things. Like one is data written to the log files, right? And you can see in general I have an average about 1 megabyte a second written to the log files. Now, but how can we think about where log space and log buffer is good enough? I like to think about that in terms of time. For how much time does it last? And we can see what in average here, the time for in memory buffer is good enough for 52 seconds, right? 52 seconds in memory, that's long time if I am flashing it every second, right? I mean, there is several standard deviations, right? Enough spike for all the spikes and so on and so forth. And also we can look at the time for redo log space, right? And in this case, we can see we're getting it for approximately an hour, right? Which is, again, so circling through logs for an hour, right? That means we can delay the writes for dirty pages for an hour. Again, that is a long time, so that shows healthy. If you'll just have like a couple of seconds here and 2 minutes there in the log file size, then that would be another indication what you probably want to increase the sizes. Now, in DB.io, in this case, that is something what we would look in terms of a disk I/O. Often that is where a majority of disk I/O comes from, and that will match the numbers you would see from vmstat or from IOstat numbers. The good thing here is that you can also see how many data fsyncs and log fsyncs you are getting, right? That's additionally to the read and write operations. Now, another thing what we have here is for many workloads, you may want to understand, okay, now we talk about their question of number of rows processed or even handler calls, but what really tables are being accessed? And in this case, you can, through their table statistics, we can show you top tables by amount of rows read from them, as well as by updates. Right, so you can really understand what the hot tables are, and often when you would see some sort of spikes, you would go to this dashboard and see, oh, look at that, for some reason this table became extremely hot, right? And that can often give you some ideas what to look at. Another way to look at that is actually through performance schema. In PMM, we provide 2 ways to look at this data, through user stats and through performance schema, which provides similar statistics. If performance schema actually given us a little bit more information, we can see in this case how much time was spent fetching the data right from the table. Right, fetch, that means read pretty much, right? Updating the data or inserting the new data, right? So if you have performance schema enabled with this instrumentation, you can even get more details. We also can see the most active indexes, right? In this case, which indexes are being used for read, right? Especially when you look about their inserts, they say as no indexes used, right? But we can also see indexes for the delete, update, which is very helpful to understand which indexes are hot in our workload. Now, we spoke a high level, in general database, what tables. Now you will say, hey, can you figure out what queries are doing all this kind of messy stuff? And yes, we have an application built in PMM, which called Query Analytics, which allows us to see what exactly the top queries are, with a lot of additional information, like how many queries per second we are getting of this particular pattern, to get a little kind of spark line to understand, is that kind of sustained load, or is that coming something goes ebbs and flows. You can also see how the latency changes for this query, and so on and so forth, right? And that is a great tool if you want to drill in what's going on the query levels. One thing I would also encourage is to take a look at this little graph, which shows us information about the latency details. Average latency may not be enough, right? Averages in general is not very good measure, right, for detailed performance. And for example, for this case, I look at the commit query and I can see, hey, you know what? Average is 12 milliseconds, but actually there were some stalls. I guess what some commits took up to 7 seconds, right? Wow, that is, and important to know that's quite a variation, right, from our average. Even 95th percentile is 10x more, right? So in this case, I may need to look into that stuff. Why do I have so high variance, right, between the queries? Now, as I mentioned, top queries are queries sorted by their load, right? Load is pretty much the same concept as used elsewhere, right, which is computed by number of queries which are multiplied by their average, the average response time, right? That's how you can think about that. So it's described here. Now, what is a good thing to understand? The load in this application doesn't mean what that query is guilty, right? It simply looks at the response time kind of contribution. It's very possible that you have a query which took a lot of time because it was spent 90% of time waiting on a row level log, right? So it was victim rather than offender, right? So in this case, we don't show a difference, but typically as you look at the query details, you've been able to sift through who is guilty and who is just a victim pretty quickly. So let's look at this thing, which is our service summary example, which gives us a very good overview about how overall server is executed, right? And that's pretty much combined stuff for all queries. So for example, from this stuff, I can say, hey, you know what, in average, the query execution on the server is, 77 milliseconds, right? Whatever, good or bad is, but that gives us some very good high-level numbers, right? And I can see what in average queries, for example, don't spend, spend about 32 time waiting on disk I/O, right? So we can judge from that to what extent this load is I/O bound versus CPU bound. And I'm saying, well, that's probably, guys, hard for you to see. I should probably, give some lighter colors, right, for stuff next time. Okay. So whole server summary number 2, there are more information about the details. We provide a lot of information about the load, right? Like how many temporary tables are we using, what are the size of those temporary tables, and so on and so on, which gives us a very good summary of a workload for a whole server. Now let's give a couple of more specific queries example. So in this case, that is an update query. In this case, I can jump here and say, hey, you know what? We have about 5% of a query time. We have actually 23% of a query time came from log, and 5% from InnoDB row level log, right? That means for some reason this query was impacted by the table logs, right? For one reason or another. Or we can see what is 17% of a query response time came from waiting on disk I/O again. That gives us a lot of good pointers about what to do with that particular query. Example for expensive select query, that would be another optimization tip. So we can see from this query that's actually have been quite rare, right? We have like really less than one query per 100 of seconds being run here in this case. But we can see what that query reads a lot of data, and that is very expensive because we have, for each row sent, we have more than 20 millions of rows examined. That is a very good metrics which tells us whether queries are really expensive or not. Now, not all expensive queries means that they have missing indexes, right? For example, it is very possible that you have some group by query we just have to crunch through many rows to get a result, right? So in this case, it's actually like a test query, but it does design so each of them aggregates 30 million rows. So it is not surprising, but in average, it really scans a lot of rows to provide result, right? But in general, looking at number of rows sent per number of rows examined, that is a very good metric how you can see wherever this server in general has good optimized queries or not, right? If that number is like many thousands, then probably you can do something, maybe add some more indexes or maybe avoid queries like that, because you know what? MySQL is not good aggregating millions of rows, right? It's just not designed for this kind of stuff, right? It cannot parallelize those queries. It doesn't have like a column store engine. Yeah, just better engines exist for if you need to do stuff like this. We also provide explain. In this case, both JSON explain and your kind of normal standard explain. I like JSON explain because it provides us a lot of very detailed information about the query execution, much more detailed than your kind of conventional table explain. And each and every version really has increased the amount of information which is available out there. Okay. Yes. So we also can have the now tool in PMM called Advanced Data Exploration Dashboard that really allows us to look at any metrics, and there's like really thousands of them which PMM captures, and really compare them among different hosts or look at specific of them. So in this case, for example, I can see what on my fleet, for some reason, init buffer pool size is not uniform. Sometimes it's 8 gigabytes, sometimes it's only 128 megs. Wow, that's probably inconsistency, and I have to do something about that. Now let's look at a couple of case studies, right? What we have done in terms of impact. So in this case, I run the sysbench, injecting kind of 1,000 transactions a second in the database, and we're going to impact how sync bin log and zero and how durable init flash log transaction commit impacts what's going on. Now, the first thing which is interesting is if you increase durability, we don't see a lot of I/O increased, right? And that that is quite interesting, right? You would imagine, oh my gosh, you have to have a lot of more I/O. Not really, right? Not at least in terms of a throughput. But what we can see in our saturation metrics, where they have a I/O load really spiked a lot, right, compared to the one when init flash log TRX commit was 0. If you look at the disk I/O latency, we can also see what there is a huge spike in both reads and writes. This is me using Samsung SSD, which doesn't really like a lot F-Syncs, right? And F-Syncs really make it to impacts both write performance, which is kind of here, as well as read performance, while reads are not really, I mean, we're not doing a lot more reads if you're just changing the init flash log TRX commit, right? Now what we can see also is the change in number of disk I/O operations, which is substantially more significant in this case than a bandwidth, right? Because now we have to flash in logs with very small blocks, and we can see that we can see here what the disk load now becomes much larger contribution, right, to disk I/O performance. And disk I/O utilization, which was pretty much nothing, right, it comes to close to 100%, right, in this case. Another thing what we can see from this change is what disk I/O size, which was relatively bulky, dropped significantly. Why? Well, because now we have syncing logs, like a very small transactions, right, maybe a couple of sectors at a time. Now, what I want to show from this stuff is what if you look at like one relatively small change, one parameter change, right, has a lot of those impacts, and we can use this tool to really get a lot of insights from different dimensions what is going on. Now let's look at the MySQL size. Now what we have right now is we have a spike of average threads running and especially peak threads running. Why is that? Well, because if you have a transaction commit taking a lot of time, then I have transaction latency increased, right? And I have to have a high concurrency to serve the same number of transactions coming in. Make sense? Right? Now, something what you may be surprised in this case is this, right? Well, if I say I inject the same amount of transactions, 1,000 a second, why number of MySQL questions increase? Any takers? Anybody would suggest? Any suggestions? Okay, well, I'll move on because I don't have too much time, I think. Yes, and the nice lady on the back says she will just, kick me out of the room, right, if I don't finish on time. So, yeah, the reason actually is deadlocks, right? So this tool works how actually your application should work, right? If you encourage a deadlock, you have to retry, so you can still serve user transaction. And in this case, we almost had a very little deadlock, but now when we have transactions start to be slower, there is a lot more conflicts, and number of deadlocks increase absolutely disproportionate, like 10x or more. Right? That is also a good illustration to say what relatively kind of a lot of impacts, they are non-linear, right? As we can see here. Now, what we said here is what we have more deadlocks because we expect longer row lock waits, right? That's our speculation. Here is we can see that, right? What we have number of row lock waits spiked, like a lot more collisions, and an average collision is now much longer than it was, right? And of course, a row lock weight also is high, just kind of a little bit harder to see on this scale. But if we zoom in, we can see what our load, which was pretty much nothing, to now getting to, in average 7.5 transactions at the time are waiting on rollover locks, right? Which kind of a lot. Here is another thing which is interesting. As I mentioned, we are flashing at the transaction commit, right? Every transaction commit, and this is a scene-based bench. It's used very small transactions, and what we can see here is what we almost use a no-log buffer, because it's kind of flashes every time as quickly as there is just, a couple of kilobytes of log records, right? So another impact. Now another thing in this case, and I would just point out this different time here, is if you have in a DB, if you have operations like commit-bound workload, we can expect group commit to work, right? To commit multiple transactions at the same time. And we have a graph of that which shows us a group commit batch size, which you can see what in average we are committing 7 transactions of a single fsync, right? So, so pretty cool. In this case, we can see also what commit is now highest in the top, because we say, hey, that is became commit-bound workloads. Here it goes, right? In average, it takes 17 milliseconds, and that is top contributor to the load. Now, another example. MySQL 5.7 allows us to change buffer pool size. And let's do that. Let's change from 48 gigabytes to 4 gigabytes, right, at a time. Do it online and see how that's going to impact our workload. First one, we can see what number of queries kind of, number of QPS kind of dropped, and then it spiked. This is because this workload, if it cannot keep up, it kind of queues the data, right? As many, I would say, like a batch application would, for example, behave this way. So we can see what this D pretty much corresponds to this hump, and that corresponds to applications if they do a queuing. If applications would be something like a user request, then this thing doesn't happen, right? You miserable user just give up, right, and and go away. What happens at the what happened here? We have a spike in the IO load, and in general, it's later stabilized on much higher ratio, right? Because obviously, the small buffer pool, that means much more IO have to happen, which you can see here as well, right? A number of IO with 4 gigabytes buffer pool, or with 48 with 4. Significantly increased I/O. But what is also interesting in this case, we can see what we have a large spike of a number of I/O, and this is because there was dirty pages in the buffer pool which has to be flushed, right, at this point before we can complete resizing buffer pool and start working on. Another thing what is interesting in this case is what happens to disk I/O activity. And we have seen is what we have a lot more IOs starting to happen, right? But we can see what at this point in time when the resize was happening, our disk was working as fast as possible. It had a high IO saturation. We also see spikes in disk IO latency for both reads and writes. But then later on, it's kind of recovered very similar to what was before. And what we can see in this case, while we significantly increased I/O load on the disk, it's still keeping up pretty well, right, with a new load, because we don't see a significant increase in the I/O latency. In the DB deadlocks, we can see we had a spike, and that corresponds to a lot of transactions which you have to work through concurrently, and then we stabilized on a baseline which is slightly higher, because transactions now take a little bit longer to complete, but it's not as bad as it was when we had enabled durability. Another thing which is interesting in this case, for some reason we actually reduced contention with this. Right? I mean, I don't have a good explanation why we are seeing that, but at least for certain mutexes, if you do a lot of I/O, that means you don't really have to compete on the staff and buffer pool, right? Interesting data, right? We can also see what workload has become a lot of I/O bound, and we can see that here, what now 80% of I/O, 80% of a query execution times corresponds to waiting on disk I/O, pretty much what you would have expected. Okay, so you can see from that what really can find a lot of insights with a MySQL performance, right? And frankly, what I'm doing with PMM is, as I like solving puzzles, right? So if somebody comes with a puzzle, interesting puzzle of some strange behavior, I try to analyze and resolve that. And what I want to do is to make sure that there are features in PMM which allows me to use that tool to resolve those. Well, that's it. The compulsory reminder to rate my session, so they allow me to talk on this conference again next year. Yes, and thank you for all the sponsors. If any questions, I still have about 3 minutes. Yeah. What's that? Well, yes, that is a good point. Some people use that with Prometheus Alert Manager. That is one of the tasks for our team to make it a little bit easier, right, to connect to external alert manager. What we hear from a lot of folks who would like to have an external alert manager rather than built in PMM, because in many cases you would have some credentials stored in alert managers and so on and so forth, right? But that is an important thing. Thank you.
Is it possible to check who is blocking your session?
Who is blocking your session? Well, who is blocking your session? Yes, that is possible. We don't quite visualize it here, but that information is available in information schema tables. Yeah, but we don't have it built in the tool right now. Okay. Okay. Any other questions? Yeah. Okay. Yeah. So how does a long query times depend on the deadlock? So let's think about this, right? So you have your application, right? The application typically ingests certain amount of user requests right a second. Let's say user transactions. Now, if you have let's say you have 100 transactions which comes in. If my latency is low, right? Let's say I can process that transaction in 1 millisecond. Then mostly I will have only one active transaction at the same time, right? Or even 0. Now imagine if I have each of those transactions need to process, let's say, 100 milliseconds, right? 100 milliseconds, 100 transactions second comes in. That means I will need to process many of them in parallel. In average would be 10. The more transactions are being run in a parallel, the high chance they're going to step on each other's feet, right? And that is how increased latency corresponds to increased chance of deadlocks. Make sense? Okay. Okay. Yeah.
It looked like the screen interval was about 5 seconds. Does that add any load to the MySQL
So the scrape interval is configurable, right? And what we usually use, actually, we use 3 different scrape intervals. One is for show global status and initDB metrics. We get them with 1 second interval, and that is a pretty this is a very optimal or well-optimized code path. We don't create a lot of stuff. Now, we also get some other stuff on the 10 seconds interval, and things as show global variables or information schema stuff. We query that on 1 minute interval, right? So there are 3 different intervals, right, for different information. Okay, well, thank you. I hope that was helpful.